And in this occasion, we are very honored that Professor Amitava Patra, renowned scientist, is amongst us, and he will be delivering the inaugural lecture. But before that, I request Principal Maharaj to say something towards our new post students.
So, most respected Professor Amitava Patra, Director, Indian Institute of Nanoscience and Technology, Mohali, and our respected colleagues and my dear students. We are very happy to be here in this beautiful evening because amidst us, our very beloved and respected Professor Amitava Patra, a great scientist of our nation, is present. So it is a very short notice. I informed him, sir, please actually join our induction program and inspire our newly admitted postgraduate student. But he immediately agreed, in spite of his very busy schedule, because he's now in the director of very prestigious National Institute in Mohali, and as his post, he is very busy and very actually highly engaged. And all you are known that he is now the very renowned scientist, because now the latest, the Stanford University, this declaration, he's secured the his place amongst the top 2% scientists in India. And among also the physical science group, his position is 149th. So it is we are very lucky that sir, especially Professor Amitava Patra, such a great scientist, is before all of us. Especially, I tell the student that you are very lucky. So let us all join in this beautiful evening, in this interaction session. Especially, I tell the student, you wholeheartedly participate in this program. You interact with our great sir, Professor Amitava Patra, and enjoy and learn and actually utilize this time. So with this few words, I express my heartiest regards, respect to Professor Amitava Patra. I express my welcome to him on behalf of the student, those are present here, those are UG student, and also on behalf of our faculty members, on behalf of all the college staff. I express my heartiest regards and thanks. With these few words, I once again welcome all the students, those are present here, and those are also in the YouTube, this streaming session, actually for joining in this beautiful evening. So thanks all everybody. Thank you.
Thank you, Maharaj.
May I start?
Sir, before I request our head of the department to formally introduce our distinguished speaker, Professor Patra, C.K. to formally introduce our speaker.
Respected Principal Maharaj, respected other colleagues, and my dear students. At first, I welcome Professor Amitava Patra on behalf of our Department of Chemistry. Before requesting him to deliver his lecture, I just like to tell a few words about him. He has completed his PhD in 1993 from Jadavpur University, and then he went for postdoc in Japan for 2 years, and after that he joined CGCRI in 1996, and he was there up to 2005, and then he crossed the road and joined Cultivation of Science, Indian Association for the Cultivation of Science, in 2006 as associate professor, and then become the professor in 2010, and then become the senior professor in 2014, and he was there up to 2020, this year. And this year in March he joined the INST, Institute of Nanoscience and Technology, as director of that institute. Practically from 1997 he started getting some awards or fellowships or some prizes. And in 1997 he got the Young Scientist Award, and 1998 he went to Israel as visiting scientist. And after that, every year he got either some prize or some award or some fellowships. And in 2015 he became the fellow of National Academy of Science. In 2016 he became the fellow of the Indian Academy of Science. And in this way, in this year also, in 2020, he got some prize. In this pandemic year also, he got some prize, that is MRSI ICSC Material Science Annual Prize, and this year. And he has published about 250 publications, around 250 publications in national and international reputed journals. Practically, he has a great career. Not only that, I personally meet him sometimes, and he's a very good man. With all this, I would request Professor Amitava Patra to kindly deliver his lecture. Professor Patra, sir.
Thank you. Thank you very much for nice introduction. And do you see me, right? Everything okay? So first of all, very good evening to all of you, especially for the students and also my teachers. And I'm very honored and privileged to be able to give a talk today. And I extend my sincere thanks to Kamala Krishnandoji Maharaj ji for inviting me and for giving me the opportunity. Today, I'll discuss something about our research, what we are doing or what we try to understand last couple of years. Because you know that I am working on nanomaterials for photon harvesting. Today I'll discuss about that thing. But right now I am at Mohali. I am also associated with the School of Material Science, Cultivation of Science. So I have both affiliation. So before that, going to my presentation, I'll discuss something or I'll say something to my dear students, future generation of Indian science. So they should know that because this is the beginning of the career, they should know that the C.V. Raman worked at the oldest research institute, that is 145th years old, that is Indian Association for the Cultivation of Science. And I came here only the very new institute that is only 7 years old. So you know that C.V. Raman worked there for many years, that is 1907 to 1933. And he discovered the celebrated effect that is on 28th February 1928. That bears his name, and we celebrate the National Science Day on that day, on 28th February. And this is the only Nobel Prize in Science that is on 1930, before independence. So and this is the instrument. It's still lying at the Cultivation of Science. That is very simple, innovative instrument which lead to the discovery of our own effect. That's why I want to show all the students that for doing good science, you don't need all the time that sophisticated instrument. Obviously, you need to characterize this thing, but innovation is most important thing. So before going to the discussion part, I'll discuss something about, I'll say something, I'll share something with our students. So what is science? Science, those who are practitioner of scientific research career, science is about telling good, readable, memorable stories. And you have to learn to write clearly and consciously, otherwise nobody will read your paper. And you have to tell the story, what you are doing and what is your motivation, why you are working on that. And most important thing for a scientist is the the publish a paper, because priority of discovery in science goes to the one who published first. That's why we always follow the Faraday's very important line, quoted line, that work, finish and publish. That is the most bottom line of this research field. Now, for being a trained scientist, what should be the important criteria? So you should acquire the basics, work with the right people. That means right guru hona chahiye. So like, so everybody should have their respected gurus, and one does not need to be a super intelligent. Otherwise you will not be the scientist. That is not the right thing. But the important aspect, absolutely essential part, is the application of your mind, diligence and sense of purpose, why you are doing. The power of concentration, that is very important, what always we know from the Vivekananda's thing. So perseverance, and that is the most important aspect for being a good scientist. So to do good work, what is the important thing? That young people must strive to have an open mind, not be bogged down or something. You should open mind, don't be biased, and seek out places where there should be surrounded by first class intellectual. Otherwise you will not interact with the other people. You could not learn the things what is going on. So as a scientist, your chances of achieving anything can be greatly diminished by joining an institute that is under resourced financially, and because they does not value the creativity. That is most important part for being a scientist. But scientist life is very important. Few important things are there. You have a lot of stress is there in the scientist life, lot of rejection in your life, lot of rejection of papers, lot of rejection of recognition. That's why you have to be very patient. And intense competition right now in India, a lot of competition, lot of good researchers should come up. A lot of politics, obviously, lot of politics is in the sense of scientific politics. So you have to survive. So, and another important thing, that balancing with your family, with the work, because most of the time after marriage, after family life, people quit that job and they are not being very professional. That is the important criteria for a scientist. You have to balance between family and your work. So what would be the quality to be succeed? One thing, important thing, is the creativity, obviously the originality, imagination, intuition. That is very important for any scientist, any creative work. Persistent, that is most important thing, because sometimes you have seen that couple of people publish a good journals, then there is no paper last 5 years. That is not good. That ability to collaborate with other people, because now it's multidisciplinary, people are working on interdisciplinary work, and in breadth and depth of the science you should increase. And finally you have to be very honest on your subject, on your colleague, with everything, because the honesty is most important thing. So another important thing for doing good research, the primary aim of the research must not just be more fact or just yet more facts of strategic value. Gate contribution rarely come by adding another decimal place. That means, just if you are following somebody's work all the time, just changing some ligands, changing something, molecules, that will not give an impact. So young scientists should aspire to become established within a particular discipline, any discipline what you want. Find a project that could be identified as yourself. That is, should be always, this project is doing this. That means like nano or physical means our team is working on nanophotonics material in India. So this is the particular identified field should be there. And persistent and luck. Sometimes we are saying that luck is bad, that's why you cannot do anything. But according to Louis Pasteur, he stated that, let me tell you the secret that has led to my goal. My only strength lies in my tenacity. That is most important thing. Luck, it is true, is necessary, obviously, but the greater the number of experiments carried out, the greater is the probability of being lucky. That is very nice word. So being an experimentalist, being a researcher, you have to try a lot of times, lot of experimenting you have to do. With one or two experiments, you cannot think that you will be doing something great or something. No. So luck is there, obviously, but more important thing is that tenacity. That is most important thing. So this is for the students, those who are willing to do some good research in future in different places in India or abroad. So these are the couple of what is my understanding that I want to share with all of you. So now I'll come to the topic that what we are doing. That a couple of things I want to discuss about the light harvesting system, especially on the 2D based material, like conjugate polymer system, carbon dot or metal cluster based light harvesting system, and finally I'll conclude. So what we have learned from the photosynthesis process, the natural light harvesting system, because it is very simple equation from the 12th class, you know, the carbon dioxide or water in presence of light, that means photon, you can produce the glucose. It is very simple equation, but very complicated equation. So what is the physical chemistry behind it? Why the chlorophyll molecule is very important molecule to doing this kind of reaction? Because if you look at this spectrum, this is the spectrum of the solar light, that is from 300 to 800 nanometer. And very important thing is the different kind of molecule. This is chlorophyll B molecule absorbed at around 475, carotene, chlorophyll A is around 680. So different kind of absorption band is there, and they absorb the photon light, the sunlight. That's why they call the antenna material. And this chlorophyll, carotene, all these molecules have a heavy epsilon value, that is 10 to the power 5 per mole per centimeter, because then only they can absorb the photon, H nu. Then they can react. And the reaction, they absorb the light, the photon energy absorbed by the antenna molecule, that is the chlorophyll molecule. Then what happened? By sequentially transfer of energy, it goes to the reaction center. In the reaction center, through the electron transfer reaction, it finally convert to the light energy to the chemical energy, that is the glucose. This is the natural light harvesting system. So from where we can learn that the photon can be used to transfer the photon energy to the chemical energy. Now, what is the light harvesting system in artificial light harvesting system? People now, those who are working on nanomaterial or any kind of material science or any kind of research on different field, actually in nanoscience, last couple of years, last 20 years or 2 decades, people are using different kind of nanomaterial like quantum dot, metal nanoparticle, semiconducting metal heterostructure, semiconducting polymer nanoparticle, porphyrin nanoparticle for artificial light harvesting system. Because this nanomaterial, not molecule, this nanomaterial has a very high epsilon value, and that is very photostable compared to the molecular system. And they are able to absorb the light, and they can convert the light to the electrical energy or kind of renewable energy. Now, what is the important issue? Why people are interested on the renewable energy or artificial light harvesting system? Now, the two important major issues right now people are facing, one is energy crisis, another is global energy. Now, energy crisis, what is the energy crisis? Because you know, the 80% energy is coming from the fossil fuel. And now the global energy consumption is 16.3 terawatt, but it will be reaching very soon in 40 terawatt. But fossil fuel you cannot use so long time. That's why people are interested on renewable energy. Right, value is 14% energy will come from the renewable energy. Another important issue is the global temperature. Those who are working on catalysis, different kind of catalysis, people are working on it to efficient catalysis to convert the carbon dioxide to carbon monoxide or methane or something. Because carbon dioxide level may increase to only 600 ppm, that will increase the global temperature by 2 degree temperature. And that is the important right now, the burning problem. People are trying to develop different kind of catalysis, efficient catalysis who can convert the carbon dioxide to carbon monoxide. So these are the important issues. So now people have already developed the artificial light harvesting system. One is, you know, the LED bulb, LED thing. But what is LED? Light emitting devices, where you can convert the electrical energy to the optical energy. That is actually the mechanism is through the energy transfer process. Other important contribution on the artificial light harvesting system is the photovoltaic or solar cell, where the optical solar energy you can convert to the electrical energy, that is by using the charge transfer material. So a lot of people are working in fourth generation now, the solar cell devices, people are working on it. People, you know, that silicon wafer still in all the silicon wafer is being used for solar cell application. But now people, by using different kind of nanomaterial, they try to understand and try to make different kind of efficient devices by perovskite or quantum dot. I'll show you some examples. Now, in case of light emitting diode, what happened? You have two different electrodes because you have to put the electrical field. That electrical field from metal, that electron goes to the surface of the layer, and from the ITO it goes to the electron, and they will recombine. They will generate a light. That means electrical field you can convert the light energy. But the important aspects for light emitting devices or photovoltaic cell, that exciton binding energy is very important, and exciton diffusion length is very important, because you generate electron and hole, because electron from here to there, then electron and hole, they will recombine, they will generate a light. Because when you excite a system by the light, they can generate electron and hole. So they will recombine, they will generate a light. So in case of light emitting diode, the recombination is very important, electron and hole. That's why the diffusion length should be less. But in case of solar cell, the electron and hole you want to separate to generate electrical current. That's why diffusion length should be high and exciton binding energy should be less. So these are the important criteria. Now, in solar cell, people are using the silicon solar cell. Why people are interested to develop different kind of solar cell instead of silicon solar cell? Silicon solar cell has a problem. Silicon solar cell, this is the spectrum of the solar spectrum. If you look at this spectrum, this is thermalization process. You cannot use this solar light for your conversion to the light energy to the electrical energy. Because in semiconducting system, what happened, there is a valency band and conduction band. When the light interact with your system, that electron goes from the valency to conduction. But because of the solar spectrum of different wavelength, electron can excite from the valency to conduction, and to the excess energy, kinetic energy they can gain. Because if you excite the system higher than the band gap of your material, Then what happened? That electron goes to the higher excited state and they will relax to the conduction band. That is called thermalization process, because this is non-radiative process and that will heat up your system. That is called thermalization process. And it takes place in within 1 picosecond. What is 1 picosecond? That is 10 to the power minus 12 second. So that is called the hot electron generation, hot carrier generation. Because so far the 31% the quantum efficiency of a solar cell. But if you can extract that hot electron before recombination, you can go up to 66% thermal efficiency. So people are now trying to develop a system where you can extract that hot carrier or hot electron before recombination process so that their efficiency you can enhance. This is the now present thing, those who are working on the energy harvesting material for the solar cell. Now what is this? In right hand side in case 3, if you excite a system where exactly on the band gap, this is the EG is the band gap. So this is the light. If it exactly matches with your band gap of your system, then the electron goes from here to there, then electron recombine. This is charge recombination process. Then there is no hot carrier generation. But if you excite with the higher wavelength, then the band gap, then the electron goes from the valency to conduction, then there is a hot carrier relaxation, and that will kill your system. That is thermalization process. Again, if you are higher than the band. And we are now working on that aspect to understand how we can extract that hot carrier relaxation process by using the ultrafast spectroscopy. Now, how to overcome the thermalization process? Different people are taking different route to reduce the thermalization losses. One is you can generate a multi-junction photovoltaic cell that is costly. Somebody is working on carrier multiplication process. This is not high enough. Now people are working on singlet fission process. I will not go into the detail. And somebody or few groups are working on extraction of hot carrier. We are also working on it. I'll give some examples. Now that is the photovoltaic stuff, right? Now if you are working on photocatalysis, if you are interested for hydrogen generation or carbon dioxide reduction, what you do? The thing is that very, very simple way, that same electron and hole you generate by exciting the light. If you take the electron in anode and hole in cathode, you can generate a light, that photocurrent, that is called photovoltaic or solar cell. But if you extract that electron for reduction purpose from hydrogen ion to hydrogen gas, then you can produce hydrogen gas. Or if you are interested for carbon dioxide reduction, then that hole can be used for the oxidation purpose. So lot of reaction photodegradation process you can use by using your electron and hole. So those who are working on hydrogen generation or carbon dioxide reduction, they are interested on the right hand part, and those who are working on the solar cell application, they are interested on left hand part. So these are the basic fundamental things. And in our group, we are working on two photon spectroscopy material, carbon dot material, conjugated polymer system, organic, inorganic hybrid system, metal nanoparticle, 2D structure and perovskite, and finally we are working on the clusters also. So now I'll give you 3 examples. One group of people are working on carbon dot, perovskite and conjugated polymer, because for optoelectronics application. The important thing you have to understand, very basic, very important thing, because if you increase the binding energy, because in case of polymer, you have a long high binding energy, means the electron and hole separation, you need lot of energy to extract that electron and hole. That's why the binding energy is very high. And if your binding energy is very high, then the charge mobility is less. That means that material is not good for the photovoltaic cell. That's why nowadays people are working on perovskite material, because it has a less binding energy. That means the charge mobility is high, so that you can extract that electron and hole and you can generate a photocurrent. That's why people are interested on perovskite. This is a very recent emerging field. People are working on perovskite. Maybe you heard. And also in quantum dot in between the perovskite and polymers. Why it is important? Because after excitant you can generate electron and hole. If you have weak binding, then they will go in a long way, then they will recombine in the defect structure if you have, or this is kind of recombination process. But if you have a strong binding, then they will not separate it, and this strong binding is very important for LED application, light emitting device, because you want to generate light by recombination of electron and hole. So different kind of mobility, different kind of binding energy you have to know for different kind of material, so that based on your requirement you choose this kind of materials. Without understanding this basic thing, that excitant binding energy or mobility, you cannot use this material for any purpose, any devices. People are working on different luminescence nanomaterial. We are working last 10 years, 20 years, and different issues are there, that exciton generation, hot electron dynamics, Fred process, Foster resonance energy transfer, light harvesting system, protein nanoparticle interaction, different biointeraction, nonlinear optics, photodetector, photovoltaic. I'll not discuss, but we are working on that using the luminescence quantum dot. The most important aspect in the nanoscience is that, as it is a multidisciplinary subject, so basic thing is that you have to design a nanostructure material with tailoring the property. You have to tailor the property. You have to tune the optical emission wavelength by using your chemistry knowledge. Without chemistry, you cannot cook your nanomaterials. But to understand their functionality at very fundamental level, you have to by using your physics knowledge. That too subject is very important if you are working on nanoscience. If you are working on nanobio, then you have to have a knowledge on biological stuff also. That I'll not discuss. Now, what is the semiconducting quantum dot? Why it is quantum dot? Why it is not nanoparticle? Quantum dot, when the nanomaterial is very close to the Bohr radius. So every material has their own Bohr radius. Like then they follow the quantum confinement rule. That means like a particle in a box, when you reduce the size of the box, length of the box, the potential energy will increase. You can tune the emission band or the band gap of the material. If you change the band gap, that means you can tune the emission property. As for example, this is a solution of cadmium sulfide in daylight, but when you excite by the light, that will generate a green light that is in particular size. Now the question is that you use one photon for exciting this nanoparticle, you will generate one photon. That means the quantum unit should be 1, because one photon absorption, one photon emission. But if you measure the quantum unit should be very less, because all photon will not emit what the photon excitement of this. So what is the reason? Because this is a semiconducting system, there is a valency band and conduction band. When the photon interact, this valency band goes from the valency to conduction band, and they will recombine and they will generate a light. So it depends on the band gap, you can tune your light. But this is a radiative process. The recombination, one photon absorption, one photon emission test. But usually it does not happen. There is a non-radiative process. That electron goes to the trap state or defect state, they will recombine, they will not generate a light. So quantum is a combination of the radiative and non-radiative process. If your system has a lot of non-radiative process, then that will not generate a light. That is a non-radiative process. That's why you will not get any light. So always go for a radiative process. So we try to understand whole kinetics, what is the lifetime, how it will recombine, all the dynamics process by using in the nanosecond time scale, because in the nanosecond time scale you can get it. So what is the fundamental processes for light harvesting system? Important three processes you have to understand. Photophysical process. One is exciton dynamic. That means that electron grows from the valence to conduction band. They will recombine. This is a radiative recombination process. Otherwise, there is a non-radiative process. That electron grows. They will non-radiatively interact. This is a non-radiative. So, whole the relaxation process you have to understand by the time result spectroscopy. Otherwise, you cannot design your nanomaterial if you don't know the relaxation process. Other is the charge transfer process. Why it is important? If you are interested in photovoltaic or solar cell application or hydrogen generation, then what happened? You have to have a heterostructure, A and B system. Then when you excite by the light, that electron and hole will be excited, and that electron can transfer or hole can be transferred. There is a charge transfer process, or you can extract that electron and hole to generate a photocurrent, right? So that charge transfer process is very important. That whole kinetics is very important. How the electron first, what is the kinetics, how it first goes from one state to other state, that is very important. And finally, the energy transfer process is another important thing, because in your M.Sc course, maybe you will go for energy transfer by the FET process, Foster energy resonance transfer process, where there is a donor molecule, there is an acceptor molecule. If you excite the donor molecule, that energy can transfer to the acceptor molecule. There should be overlap between the emission band of the donor and associated band of the acceptor. So recently we try to understand the hot electrode extraction process by the ultra fast kinetics, that is femtosecond time scale, that is 10 to the power minus 15 time scale. So I'll show you. This is the valency band and conduction band. So if you excite in this band gap, then there is no problem. Then, or if you excite higher than the band gap, that this electron goes from here to here, then what happens? This is the hot electron. This electron you can extract by the suitable acceptor or anything. So this kinetics, it takes place in less than 1 picosecond, these kinetics. But second step is that can relax before extracting, that can relax over here. That is hot carrier extraction process or cooling to band edge or from hole. Or third process is that electron you can take it from here to here, extraction of carrier from the band edge. That is the cold electron called, and that is called hot electron. So all these processes, it takes place, and this recombination process takes place in nanosecond time scale. This extraction, it takes place in femtosecond time scale. This takes place in picosecond or femtosecond time scale. So if you have the femtosecond time scale time resolved system, you can understand all the carrier relaxation dynamics. I'll show you a couple of examples. So what is transient absorption spectroscopy? Very not very tough. There is an absorption band, Lambert's Beersley, there is an absorption band. By using the photon energy, it goes from the ground state to excited state. This is the ground state bleaching, and we try to understand this bleaching kinetics from where this I don't want to go into the detail, but this is the kinetics from the transient spectroscopy you can understand. And from the, if you have the growth kinetics, then you can understand the hot carrier relaxation process. If you have the bleaching recovery kinetics, from where we can understand the recombination process. I'll not go into the details, but this is one example recently published in 2 years back. This cadmium selenide nanostructure material. This is cadmium sulfide rod and cadmium selenide dots over there. Why we have done it? There is a band diagram. This is a cadmium sulfide band. This is cadmium selenide. Because this is a quasi type 2 band structure, because if you excite this, then the whole heterostructure, that whole goes from the cadmium sulfide to cadmium selenide, and this all are delocalized over here. So there is a chance of transfer of charge transfer, and you can separate the electron and hole. Why? Because this material I want to use for hydrogen generation by using the catalysis. Another thing, same material, whether we can extract that hole and electron for photocurrent generation, that is for photovoltaic application. Now I'll show you. This is the hydrogen generation we can generate by using the same material. You can generate a hydrogen gas. On the other hand, same material can be used for photovoltaic. This is for solar cell application. I'll not go into the detail of the mechanism. Now, by using the ultra-fast spectroscopy, we try to understand all the relaxation process, hot cooling process that takes place 453 femtosecond, because we have seen that cooling dynamics of hot electron is very slow in certain composition. That's why electron and hole are more separated, and if it is more separated, then that electron and hole used for reduction and oxidation purpose, or they can generate a photocurrent. So that ultra-fast spectroscopy can give you a idea that what kind of relaxation process is. That's why the spectroscopy part is very important in material. All physical chemist people are interested. Spectroscopy means only the physical chemist people want to use by using some molecule. But in material science, you can understand a lot of fundamental important photophysical processes by using the ultrafast spectroscopy. This is one example, that alloy nanocrystal, that is pure nanocrystal, because we want to see that whether the hot electron carrier cooling dynamics we can control by changing the composition of a nanocrystal. And very interesting thing is that in solid state you will see that different crystal structure, because in cadmium selenide different kind of cubic crystal structure you can tune the. Even here we have shown that the crystal structure and lattice strain also influence your hot electron cooling dynamics by using the ultrafast spectroscopy, and that can be very useful for your designing of your device materials. Now I'll discuss about this is so far I discuss about the quantum dot, where you can change the size and you can tune the color from blue to red to green by changing the band gap. But this is a 2D semiconducting nanoplate. This is the band diagram where you have the heavy hole and light hole, because this band diagram it's parabolic, because quantum one directional, because it is 2D structure. In that case, we have seen that if you change the layer, number of layer, maybe 2 layer, 3 layer, 4 layer structure, you can tune the emission band, that is 3 layer, 4 layer, 5 layer, from 450 nanometer to 600 nanometer. You can tune from blue to green to red, because there's another interesting thing is that why we are interested recently on the 2D semiconducting nanoplate, because this is very narrow emission band. Narrow emission band is very important for lasering application and for LED. And that binding energy of this 2D structure is very high compared to the quantum dot. And if it is the binding energy is very high, that means electron and hole you cannot separate very easily. That means that electron and hole decombination process is very fast because of the high binding energy. And this material can be used for LED application. We have published a couple of papers this year. So this is 3 layer, 4 layer, 5 layer structure from the X-ray we want to confirm, and this structure 1.25 nanometer, 1.5, 1 nanometer. I will not go into this detail. This is the 3 layer, 4 layer, and 5 layer system. So whole relaxation process we have seen that you can control if you make a heterostructure, because I want to extract that electron from the 2D structure, otherwise you cannot extract. In presence of graphene oxide, we have seen that PL intensity decreases because you can extract that hot electron from the 2D structure to the graphene oxide, and you can generate an electrical current. So here we have absence of the graphene oxide. This relaxation process, hot electron relaxation, 800 picosecond it takes place. But in presence of graphene, it goes down to 400 picosecond, and the electron transfer rate is 1.4 picosecond to the graphene oxide. That means electron you can separate from the 2D structure, and this you will generate a photocurrent. And recently we developed for 3 layer, 4 layer, 5 layer structure, the ultra fast cooling also you can control for 100 femtosecond. Why we are interested? We develop different system also with the gold cluster, because by theoretical understanding we try to understand what is the electronic interaction with the gold cluster or molecular system with the 2D structure, what kind of band gap. We have seen that the Fermi level will change and it goes from the close to the valency to conduction band, and that will create the charge transfer takes place. And in this heterostructure system, we generate a photodetector, because silicon wafer is being used for the photodetector in the visible range. But interesting thing is that in this system, we generate a 350-fold enhancement of the photocurrent and a very high detectivity value, that is 10 to the power 11 joules. That is very close to the silicon wafer. So this material can be used as photodetector, and photo response is 200. That is very promising material. So 2D structure based material can be used for optoelectronics application. As a proof of concept, we have shown that this material can be used for photodetector. This is another material with the perovskite. We want to see whether the extraction of the hot electron can tune by of the perovskite. This is the perovskite nanocrystal, and we have seen the extraction of hot electron carrier you can control from the 800 femtosecond to 130 femtosecond, because this is very important to understand your design of the device, so that your efficiency you can enhance because of the ultra fast electron transfer process. So these are the fundamental thing we try to understand. I will not go into the detail, but I'll give it. And recently we wrote a review article on chemical review that what is the important challenges, what is the current important issues of this nanomaterial for different kind of light harvesting systems, especially for photovoltaic or solar cell application, and also for hydrogen generation, carbon dioxide reduction. What is the important challenges behind it? Now I'll discuss about little bit on the semiconducting conjugate polymer nanoparticle. You know the conjugated, you can even here you can tune the light from blue to red by tuning your length of the polymer, or if you dope some dye molecule inside the polymer nanoparticle, you can tune it. But these are the important issues we try to address: charge transfer, energy transfer, exciton dynamic, exciton diffusion. This lot of things. What is the drawback of the quantum dot, and what is the advantage of, because it is very useful for the biological imaging purpose, so that there is no degradation. And polymer is conjugated polymer. Another advantage is that there is a pi conjugated system. So what happened here, there is a lot of antenna molecule here, so a lot of photon can absorb by individual chromophoric unit, because conjugated polymer is basically a multi-chromophoric system where pi electron are very much delocalized over the chain length, because if you increase the chain length, you can tune the exciton diffusion length and all relaxation process. So you know this energy level diagram Jablonski, because of the molecular system, the S0, S1, S2, Sn state, right? I'll show you the difference of relaxation process when it is aggregated structure or polymer nano. That I'll show you the exact we have measured for different systems. So this is the energy transfer process. You have to have an acceptor molecule. When you excite the donor molecule, that energy transferred to the acceptor molecule, it follows the 1 by r to the power 6. This is called pressure because of the dipole-dipole interaction. In case of nanoparticle, it is very important because of the large size, so it should have multiple acceptor, not 1:1 interaction. That's why number n is there. So if it is a 1:1 interaction, then N is 1. In most of the biological system, people are using one donor, one acceptor. In that case, N is 1. So in case of nanoparticle, you can enhance the efficiency of an papers we reviewed on polymer nanoparticle. Now I'll give you one simple example. This is MHPPB, that is very important molecule for the optoelectronics or OLED, organic light emitting devices. And here what happened, we have seen that if you put in THF solution, because polymer is very much good solvent, THF solvent, but if you put the water molecule 10% water, you get the fiber-like structure. But if you have that 75% or 20, this is the nanoparticle formation. We try to understand the mechanism of this, a very fast process. You cannot understand kinetically. Simulation, we try to understand. In case of 10 weight percent, after 90 nanosecond, we will get the fiber-like structure. But in case of 75%, we will get an impression that is exactly matches with our experimental result. But what is the important phenomena? Why the photophysical process? What kind of changes? Because in extended polymer, when it is dispersed in THF solution, that is called extended state, then all the chromophoric unit looks like this. And when we excite that electron goes from here to here, that is called intrachain energy transfer process. But when it is a nanoparticle, then what happened? This is a collapse state. Then there is a conformation summit with their interchain space. And by using the ultrafast anisotropic study, we understood that in case of nanoparticle, is interchain energy transfer takes place by using ultrafast spectroscopy, because of restriction of rotation of the chromophoric unit. I'll not go into the detail, but I'll show you something that it is in when it is a polymer nanoparticle. I'll not, because I'll tell you for the students, because in molecular system, what happened? You can excite from the ground state to excited state. They can have a sequential emission process, or you can have a parallel. You can excite this, then it will come down from the excited state to ground state, then another photon goes to this phase. But in Jablonski diagram, we are only considering the sequential model, but we never considered the parallel model. But using these both models, sequential and parallel, there's a lot of combination, very complicated relaxation process that we call the global and target analysis. In India, we are the first people to understand all the relaxation process by using this model, targeted analysis by using the ultrafast spectroscopy. I'll give you one example. This is the extended form, MHPPB in P3HT in THF solution. This is a ground state. You look this value, this S1 state, the lifetime is 480 picosecond. And then comes to the triplet state, from the triplet state to here, ground state. But when it is a nanoparticle, you will see the S1 state is 2.8 picosecond. It comes down from the 480 picosecond to 2.8 picosecond. Stuff, when it is a nanoparticle formation, there is another state they have developed due to the interaction of intramolecular interaction. In self-assembled structure or nanoparticle, they have new state they have generated. This is collective state, and we have identified experimentally that relaxation process is totally different not like a simple molecular system. So this is our and we publish this kind of papers. So tell what is the mechanism, how the electron transfer or energy transfer takes place from the polymer to nanoparticle. All the detailed mechanism, detailed relaxation process we understood by using the transient spectroscopy as well as by feeding global and target analysis. So this is one process, because most of the time we said the excited state energy transfer takes. But what is it? It comes from S1 state or from CL state. Here we have observed from S1 state to it can go to the gold nanoparticle or from CL state to. So all the quantitative data we have done it by using the spectroscopy. And this is the energy transfer process because I have already talked. This is energy in femtosecond, picosecond time scale, electron transfer in picosecond, nanosecond time scale. This is one system we have developed. This is polymer nanoparticle. This is protein molecule. Inside the protein, that is a porphyrin molecule. Here we observe that ultra fast energy transfer and electron transfer in both system, like a real artificial system, because most of the people develop a device either electron transfer process based on or based on the energy transfer process. But here one system we develop a light harvesting system where we have both electron transfer and energy transfer takes place. So this is one system. This is, I'll show you. This is the dye molecule inside the polymer matrix. We try to understand how the energy transfer takes place from the polymer nanoparticle to the dye molecule. This is Nile red dye. So we observe that it can from the S1 state, excited state, from S1 state or CL state. There is 20% energy transfer, 30% or 25% energy transfer. So without having that detailed analysis of the relaxation process, you cannot give a mechanism. You can give a tentative mechanism from the excited state you have. Now I'll go to the clusters, metal cluster. We are very much interested to understand the relaxation process of the cluster. It is in between the nanoparticle and molecular atomic state. You can change the number of atoms, you can change the ligand, you can tune the color from green to red, all this stuff. So this is one cluster copper, only 7 atom of cluster and 3 number of ligands by MALDI. We try to understand, we measured it by using the MALDI, we identified the number of atoms, and from the DFT calculation we measured the homolomo gap, and this is the homolomo gap 3.0 eV, because there is no sharp absorption over here, and but sharp emission is there. This is green emission by homolomo, and this is the excitation independent, so there is no defect structure over there. So another important cluster, recently last year we published on the, this is another important topic, aggregated induced emission, and here copper 34 clusters and copper 25 clusters, number of atoms, and all these characterization we have done. And we have seen here that in case of copper 34 cluster, we have seen the aggregated emission. That is, you can enhance the emission property in presence of solvent. But in case of copper 25, only the blue emission. In copper 34 or 32, it is a red emission. So you can tune the emission from blue to red, and you can enhance the emission property. You can enhance the quantum yield by using this molecule, by changing the number of atoms. So now we try to understand the ultra fast dynamics. That is one paper, Jing's group in America. They have recently reported on ultra fast relaxation dynamics of metal nanoclusters. We have also done something. We are trying to understand the relaxation process, but it is unpublished work. So last year, 2 hot articles on perspective on nanoscale on fundamental understanding on the electron relaxation process on the nanoclusters, especially the metal cluster we have published. If you are interested, you can go through it. Last one is the carbon dot. Because all the students may know that only carbon has two allotropes on graphite and diamonds. In fact, in our life, we know only the two allotropes of the carbon. One is graphite, pi bonding, sigma bonding is diamond. But nowadays, if I ask you, this is wrong answer. So a lot of allotropes, it can be graphene, it can be graphene oxide, it can be single wall tube, carbon tube, it can be carbon dot, it can be fullerene. You can 0D to 3D structure, you can develop nano allotropes, lot of. But interesting, our interest, because we are working on the light harvesting system, so fluorescent nanometal, we are interested. That's why I'll talk about the carbon dot. Carbon dot is very interesting and very difficult to understand, obviously. Those who are working on biology, there is no toxicity. That's why people develop different carbon dot from blue to red by very simple, by citric acid, from glucose, you can develop carbon dots. And you can have use for biological application, for energy harvesting, for catalysis, for sensing application. This is not our work, this is our work for energy harvesting. But two important aspect here, one group of people, they are interested to develop excitation dependent emission band, but few people are interested on excitation independent. Because if you have a lot of defect structure of the carbon dot, then that could be excitation dependent. And if there is no defect structure, very clear nanomaterial, then it has a excitation independent. And again, another review article on carbon dot, we try to emphasis on what kind of structure. If it is a pyrene graphitic like structure, then there is no defect structure. But if you don't have a graphitic and lot of functional group is there, then is lot of surface defect. So lot of fundamental understanding on the relaxation process is important to understand why this emission comes. We are also studying to understand the very deep understanding on the relaxation process of the carbon dot using the ultrafast spectroscopy. I will not go into the detail. So this is the model we develop by using the target analysis, what is the relaxation process, whether they have a triplet state or not. But in most of the cases, there is no triplet state, but sometimes, but they have a different level of thinking. So they can control the relaxation process. And finally, the last slide is that light harvesting system we develop by the combination of the carbon dot and gold cluster. You can tune the white light. White light generation is very important topic nowadays by changing your composition. So here what happened, if you add the carbon dot with the gold cluster, there is an energy transfer takes place from the carbon dot to gold cluster, that is only 63%. But to enhance the energy transfer process, we add some dimolecule as a bridging dimolecule to couple with the carbon dot and gold cluster. And in that case, we have a cascade kind of energy transfer in presence of protein molecule. This is the base of protein. And we enhance the energy transfer process, that is 83% energy transfer takes place. And you can by controlling the composition of gold cluster and carbon dot and the dimolecule, you can generate a white light. So this is the overall view what we try to understand. Our interest is to understand the photophysical processes by using the light harvesting, by using the ultrascopy. In conclusion, I can say the fundamental understanding of the carrier relaxation process of the nanomaterial for hybrid system is a very emerging field for making a different kind of artificial light harvesting system. And interesting findings that reveal that charge transfer in 2D structure. Recently, we are working last 2 years, not only MOS2 or graphene oxide, because 2D structure, if you put in the Google search, always you will get the graphene or MOS2 or WS2. This is people, there is a crowded field. search on 2D semiconducting nano platelet, you will find only a couple of people. In India, we are working on that. But carbon dot and gold cluster people are working here, couple of people are working in India. But our specialization is understanding on the ultrafast relaxation process of the carbon dot and gold cluster to have some make some device for light harvesting system. Finally, I must acknowledge the DSRC Unilever private company project, SCRB, DST, and these are the important things. Otherwise, so we have right now we have 12 students in cultivation of science, because they are working there day and night, very bright students. And without their help, I cannot do. I can have some ideas, I can ask them to do, and they are very brilliant. And most of them, this person, they are from either Narendipur or Belur, or yes, Narendipur, Belur. We have couple. This is from Belur. Is from Narendipur. This is from Belur. This guy, a similar thing. So. So finally, our interest is lighting the way to technology through innovation, and there is a lot of opportunities for nano research in nanoprotection biophotonics. And thank you very much for your patience. If you have any questions and queries, you can ask me right now. Thank you very much. Hello. Hello.
Thank you, sir. Thank you, sir, for your wonderful lecture. So, as you have suggested that students can ask some questions if they have some queries. So, I would request students to ask anything if you want to know more. Please ask.
ছেলেরা কোশ্চেন জিজ্ঞাসা করো।
Rajesh has question. Rajesh Singh.
রাজেশ,
You have to unmute. You have to unmute, otherwise I could not hear. Rajesh.
if any problem, you write your question in chat box, so that everybody we can, sir also can see, and everybody can see.
হ্যালো, কারো কোনো কোয়েশ্চেন আছে? স্টুডেন্টসরা তোমাদের যদি কোনো কোয়েশ্চেন থাকে স্যারকে বলো, বা মহারাজ যেটা সাজেস্ট করেছেন যে লিখে পাঠাও চ্যাট বক্সে, তাহলে আমরা দেখতে পাবো।
তুমি কেউ বাংলাতেও কোশ্চেন করতে পারো, স্যার নো ভেরি মাচ বেঙ্গল, স্যার বাংলা ভালো জানে,
Yes.
তাই হবে।
Yes.
কোশ্চেনটা ইম্পর্টেন্ট।
I think there is no question.
I think this is students are a bit scared. I
No,
think
no,
it's the first day,
no, no, ঠিক
and
আছে, ঠিক আছে, no problem.
Maharaj, then should I end or?
Vote of thanks. I can vote of
Since students are not asking any questions, so I think it is the very first day as a postgraduate students. So I think a bit scared. So
No, no, it's okay.
from the on behalf of the institute and on behalf of the Department of Chemistry, uh, I express my gratitude to Professor Patra and for sharing his work, wonderful work, the state-of-the-art research work with us, and introducing our students to the fascinating world of light harvesting. And in this lecture, he has got so many materials and so many aspects of light harvesting materials. So it's a really fascinating. We sincerely hope that some of our students will definitely join his group and
Right.
will do full research. And thank you, sir, for spending some time with us.
It's
And
my
also,
pleasure.
I thank you our teams for arranging this meeting. And I personally tender my apology because I was facing some problem initially to connect.
No, no,
Sorry,
it's
sir.
okay. No problem, no problem. No problem.
That pandemic is over, you will personally visit
Right,
us.
right. I visited couple of years back. Yeah. Sure, sure. Thank you very much. Thank you.
আপনাকে আবার আমরা সবাই কংগ্রাচুলেশন জানাচ্ছি 2%
Thank you. Thank you.
এটার জন্য একটা
Thank you very much.
কংগ্রাচুলেশন
সবই ঠাকুরের আশীর্বাদ।
হ্যাঁ না এটা আমরা শুনে খুব আনন্দ পেয়েছি যে আপনি টপের মধ্যে আইএসএস এর যে তার মধ্যে আপনি একজন অন্যতম। এই আপনার র্যাঙ্কিংও খুব খুব ভালো সাইটেড হয়েছে তারা এই আর কি।
থ্যাংক ইউ ভেরি মাচ। থ্যাংক ইউ।
স্যার ভালো থাকুন, পরে আবার এদিকে কলকাতায় এলে নর্মাল হলে আসতে হবে।
শিওর, শিওর। থ্যাংক ইউ। রাখি?
হ্যাঁ স্যার।
ওকে।
ঠিক আছে, তাহলে আমরা লিভ করে যাচ্ছি।
হ্যাঁ স্যার আমরা